Welcome to the fourth video in this lecture series. So we will discuss optimizations and the memory system. So modern CNNs are huge, right? So if you look at ChatGPT 4, it has apparently 100 or 175 billion weights. So clearly even the small ones have millions of weights and the large ones also have a lot. So the inference times are not even talking about training. So training takes weeks or months anyway, but I'm talking about the inference. So the inference times can be significant. Hence, there is a need to substantially speed up this process, which basically means identify operations that don't lead, that are ineffectual in the sense you can happily discard them without affecting the final outcome. What kind of operations would they be? Well, any convolution, any multiplication with a zero, the output is zero, so you don't actually have to multiply it, right? Similarly, if you know that the outputs of a certain region are going to be negative and then there's a ReLU layer after that, then basically you can directly set them to zero because that's exactly what ReLU does, which is that if a part of it is negative, all of it is converted to zero. Along with that, we can also look at reducing the memory bandwidth and the memory footprint, because if we have so much of data, then all of this data needs to come in. It needs to be processed and it needs to be written back. So of course, the data type, etc. is also very important in the case of a neural network. See, typically avoid using any kind of a floating point or double precision are things that you typically avoid, right? And even if you do that, you try to kind of tweak the number of mantissa and floating point bits such that you kind of store data in as compact a representation as possible. In general, for neural networks, fixed point is preferred, right? Something of the form 44.20 and so on, because you can store this as an integer and then you can do fixed point arithmetic on top of it, right? So this is kind of preferred. Fixed point in binary is typically what is preferred, right? So and furthermore, what you can do is that, so fixed point is kind of similar to quantization, and then again, depending upon which values are more sensitive and which ones are less sensitive, what can be done is that the precision of the point can be varied even within the same IF map or OF map. So of course all of that is there along with ineffectual operations. So the net result is that the memory footprint, which means the amount of memory that your model is occupying, and the bandwidth, which is the total amount of memory that is transferred between the caches and the CPU, that also has to reduce. So the weights, as I said, can be compressed. I gave one idea where you use fixed point. You can leverage redundancy in the sense if let's say the similar data repeats, so then you need not compute the convolution twice and you need not even store it twice. There is no need to store zero values, and of course you are reducing the precision of operands, which we just discussed. So the main aim is that unless there is some degree of compression in terms of storage, we will actually need a lot of space and we may not have that much of space available. So let us look at some of the ways in which a neural network computation is optimized. So one of it is common subexpression elimination, which is also a standard compiler technique. So let's assume that a part of the convolution operation, this is how it looks, right? So if we take a look at that, what we basically see, or what we basically get to see, is that we can reduce the number of additions and multiplications, because a naive approach would give us 7 multiplications and 6 additions. But I can optimize this expression. So what I can do is that I can have a single multiplication here, and I can kind of combine these w times x1 plus x2 plus w dash times x3 plus x4 plus w dash times x5 plus x6 plus x7. So as you can see that with this intelligent combining, I am reducing the number of multiplications from 7 to 3 and keeping the number of additions the same. And reducing multiplications is great because it reduces the time as well as reduces the power. So such optimizations can be done either via the compiler or via the hardware. The hardware can find these and do some on its own. Zero and negative values, as I have said, are very interesting. So if we look at zero valued weights and inputs, they of course can be removed from the multiplication process because there is no need to perform a multiplication. So what we can do is that for given a filter or given an IF map, we can store a bit vector or a bit matrix which essentially stores for each cell is the value 0 or 1, right? 0 or non-zero, right? So there is something called a binary CNN also, which I would like to discuss towards the end of this slide, right? But let's say that you can store a 0, 1 value where 0 means it's 0, 1 means it's non-zero. So then what we can do is that if both the values are 1, in the sense it's both of them are non-zero, we multiply, otherwise we skip it. So this reduces time and power, and having the zero valued weights or filters is common because the ReLU process produces them. So what happens is that the moment you have these negative outputs, negative valued outputs in an OF map, right? So the moment you have anything that is negative, right, less than 0, this becomes equal to 0 by the ReLU process. So that is why we have a fair amount of sparsity in the IF maps and OF maps. So given the fact that we can have, so given the fact that IF map values can be negative, filter values can be negative, we will produce negative values, and that is exactly what ReLU cuts out, right, and creates the sparsity. Because if you look at the ReLU function, it's like this and like this, where this is the origin. So if we can somehow get a good estimate of what the final product, the final convolution will be like, right, which is nothing but you're taking a dot product of two matrices, like an element wise multiplication. Then if we have some idea that the element wise multiplication and the sum is going to be negative, we can kind of stop the process midway, terminate it midway, and declare the result to be 0 if a ReLU layer is succeeding it. What some other approaches do is that they don't do the full multiplication in one go. They instead look at the more significant bits, which will give you a coarse idea of what the output is. So you multiply the more significant bits with each other. That will give you some kind of an estimate whether you are going towards the positive side or negative side. If you are going towards the negative side, you make a guess. In any case, neural networks are approximate computation. So you make a guess that is going to be negative and you set the value to 0. So these are all interesting techniques of reducing your computation power and time by leveraging sparsity or leveraging the fact that you think the result will be negative, which the ReLU layer is going to get rid of ultimately. So if you would recall, I had promised to explain what a binary CNN is. So the main idea is that look, what we are doing is that we have anyway decided not to use floating point or double precision in IF maps and filters. So basically, let's say that if a certain value can go from 2 to 5, what we do is we essentially quantize the range. So we say that look, we'll only consider 2.1, 2.2 like that, a fixed point, right? So of course, this is in decimal, but the same thing happens in binary. But what you could also do is you could take it to an extreme and say that look, all my input values will be binary, 0, 1, 0, 1, 0, 1, and all my filter weights will be binary. And my convolution operations, the multiplication is nothing but and addition is nothing but or. So I can kind of make a binary CNN or a BCNN, and these will be extremely fast, right? They'll be extremely storage efficient, mainly because we're dealing with 0, 1 values, can be compressed quite easily, and they'll be quite fast. So many problems, particularly in edge detection and image processing, are solved very efficiently using binary CNNs, where, as I said, the IF map values are binary, the weights are binary, and the multiplication operation is replaced with the logical AND operation. I mean, so in this case, logical and bitwise is the same, but maybe bitwise is more correct. And basically, the addition operation is replaced with the OR operation. So what are the problems with such architectures? Well, the problems are that they are not very amenable to systolic arrays, because systolic arrays is a very rigid architecture. So it wants, all your inputs to be of a certain size and certain type and so on. So of course you could quantize and do fixed point arithmetic on a systolic array. That's not an issue. But taking care of sparsity is an issue with a regular approach like a systolic array. Furthermore, if you are considering large or variable tile sizes and you want to do a lot in terms of removing these ineffectual computations, then you would rather go for the row stationary idea, which is basically, consider data row wise and then maybe look at the sparsity, and then of course have a way of encoding all of this data taking sparsity into account, and use a row stationary architecture, modify the architecture to also take compression into account. So row stationary kind of fits in well with optimizations as opposed to other ideas. And here again you could use a traditional systolic array, or maybe with modifications where you have a systolic array only for the dense part, non-sparse part, or you use regular linear algebra and you operate on sparse matrices, right? So you use the sparse matrix algorithms are very well developed. It's a very established field. So you operate on them with regular. If you go back to the idea of the doubly block circle and matrix, it will basically tell you how a CNN problem can be converted to a linear algebra problem. So in this case, we will operate on sparse matrices, again using a combination of software and hardware approaches. So this also incorporates optimizations quite well. So let's now look at methods to reduce the memory access time. So what happens is that many approaches that reduce the memory access time also end up reducing the memory footprint, right? So kind of similar schemes. So let's look at a very basic compression scheme called base delta compression. So consider four values, 100, 101, 103 and 104. So let's say I take the mean value or the base to be 102. So all I need to do is I need to store 102, that's all. And then for every value I can store the delta or the difference with respect to the base, which is -2 for 100, -1 for 101, 1 for 103 and 2 for 104. So the total amount of storage space that I would use for basically storing them is very little. And when I'm accessing memory, all I need to do is read this and then read these small values very quickly. So this is fast. Storage space gets reduced drastically, access time gets reduced drastically at the cost of computation power, which is to use these and kind of recreate these values. This also may not be required because you can use a distributive property of multiplication, and basically this will basically be equal to base plus delta times the weight. So base into weight is common, only thing that we will have to compute is delta times weight. So even the convolution operation can also be optimized using, optimized with this compression method in mind. Furthermore, what we can do is, along with this compression, we can dynamically detect if there are zero valued weights or inputs. Needless to say, we will not do any multiplications and we will not even store the zero values, but we will have some sort of a bit vector, bit map, bit matrix to indicate which locations are zero such that they are not even fetched. The precision can be reduced, so we have been discussing this quite a bit, which is that don't use single precision, don't use double precision. Instead, try to create a new number format, which is kind of an extension of existing fixed point approaches, amenable to processing in neural networks, where a limit of the spectrum is essentially a binary CNN. Needless to say, different layers would need different levels of precision because maybe the starting layers perhaps may need more and ending layers perhaps may need less. So that has to be taken into account. Different filters, depending upon what is their role, would require different levels of precision. So there's a need to dynamically study the behavior of a CNN and adjust the precision. So in this case, in the case of this sparsity, I would like to introduce something which is quite popular, known as bit serial arithmetic, which kind of is one way of taking care of the number format issues, and we will see how that works next. So consider regular like grade school binary multiplications. You have a number A and number B. So what do? The top one is the multiplicand, this is the multiplier. You look at 1, you just reproduce this number here. Then you look at 1, you reproduce this number here, 0, all zeros, 1. So what you do is that if I look at any column, what am I doing? I'm just adding, right? So what am I adding? So let us say these numbers are A1, A2, A3, A4, the bits. They are numbered A1, A2, A3, A4, so on and so forth. So what is happening is the first number here, this guy, is basically A4 multiplied with B1. The second number here is A3 multiplied with B2. So what is happening is that B2 is here A3 multiplied with B2. This is A2 multiplied with B3 and A1 multiplied with B4. So this does look like a convolution, I'm sorry, because it's 4 plus 1 is 5, 3 plus 2 is 5, 2 plus 3 is 5 and 1 plus 4 is 5. So this basically is a convolution. In a certain sense, what we are doing is that this looks like a 1D convolution because it actually is a 1D convolution. So what we are basically doing this particular thing is that we are convolving the input and the output such that the sum is 5. So let's now maybe look at this guy over here. So how is this actually produced? This is basically B2 times A4. Then the one below it is B3, alright, times A3. And the one below it is B4 times A2. So here again the sum is 6. There the sum would be 7, 8 and then 5, 4, 3. So the key idea, the key most important idea is basically like this, that what we are doing is that we are computing a convolution of these two numbers and that is giving us the multiplication in a certain sense. You can see in which sense it's happening. But the key point is that all that we are doing for each column, we are just computing a convolution. And of course, after doing that, your carry is propagating. So that part is not being captured here. But pretty much every column, the addition in every column is a 1D convolution. That's the most important takeaway point that needs to be understood over here. So given that every column represents a convolution, then you will see that in every column is a convolution. So given two bit vectors A and B, which are nothing but the values that need to be multiplied, we are treating them as bit vectors now. Essentially, we are doing a 1D convolution. The only exception that I said, or the only difference from like quintessential 1D convolution, is the fact that we are not taking these carry values into account. So carries are not being taken into account. So that is why it's not a clear addition. But if you allow the carries to ripple through, then the product is correct. So do the convolutions first and then you collect the carries, allow them to ripple through. So what we can do is that we can create a systolic architecture where basically the inputs would flow into the circuit bit by bit and you would compute these convolutions and then of course take care of the carries later. But what this suggests is that a systolic array to process these bit sequences can definitely be created because it is a 1D convolution, and then the next stage would be to let the carries ripple through, but most of the hard work could have been done by the systolic arrays for the 1D convolution part. So you can of course have a bunch of bit serial architectures, but this was the main idea, that we are using our 1D convolution hardware for multiplication, which is a core operation, right? So core operation is actually called a multiply and accumulate, because we are always kind of accumulating, into the, one thing multiplied with one more thing, we are kind of adding and accumulating, but multiplication is a slower operation as compared to addition. So the idea is that we kind of, for multiplying a by b, you read in b bit by bit. And a simple design would be that if, let's say, the bit is 1, you add a to the partial product, otherwise you don't. And then of course, as I said, another method basically would be that I have a bunch of these 1D convolution units. I will take the multiplier b and divide it into chunks of, let's say, m bits. If all of them are 0, then I can kind of discard this entire chunk. Otherwise, if, let's say, one of these bits is 1, I can compute like a partial multiplication, in the sense I can multiply this with a using my 1D convolution method, the same hardware architecture, and I can do as many multiplications as required and add the results, add the partial products to compute the final product. So let me explain with an example. Let us say this is A and this is B. So what I do is that I divide B into chunks of m bits, right? If, let's say, one of these chunks is all 0, which it can be, I can ignore this chunk. If this chunk is all zeros, I can ignore it. And for the rest, what I can do is that I can multiply them with A, and then I can use a regular bit serial architecture using a systolic array that computes a 1D convolution to get the result. But in this case, I will take sparsity into account. I will only compute that many 1D convolutions that will give me non-zero results. So I multiply this with A, and then I multiply that with A, and A also can be divided into chunks. But after the multiplication, I just add the results, the partial products, to get the final value of the convolution. So this does take sparsity into account because of this chunking. So we have discussed optimization. So let us now move to what a memory system would look like for a CNN. So there's a lot of work in this area, but we are not, delving a lot, because our main aim was to explain the notations, the maths behind the CNN, to look at the main ways that you can construct these stationary architectures, look at the hardware, the retiming lemma, and how we actually realize such circuits in hardware. So our main goal is achieved, but still some key ideas of the memory system will be discussed here. So consider a 16 cross 16 PE array. So what you need is, you need 16 streams for the rows, 16 for columns, 32 memory streams, which basically means that you need a very high bandwidth global buffer, right? A global buffer is like an L2 cache, but you need a very high bandwidth global buffer and a very high bandwidth main memory as well. So there are two approaches, a pull based and a push based mechanism, or two paradigms, which is that whenever there is a miss, you pull data the same way you have in processors. But again, for CNNs, this is impractical because it can delay our computation. Furthermore, the computation in CNNs is deterministic. You know the memory access patterns. Even if you have sparsity, you still know the memory access patterns to a large extent. So you don't have to use this. Instead, you can use a push based mechanism where your compiler and a smart dispatcher, which is nothing but a programming running on the brain of the accelerator, which is an out of order processor, it needs to kind of coordinate the computation, and it can basically prefetch data. In a sense, it can keep data warm in the caches such that it can be used, right? So you can kind of bring in data, predict it, prefetch it, keep it in the caches. and use it. So this is a push based mechanism which is based on prediction and prefetching, which in this case is far more practical because CNNs have known access patterns by and large. The only non-determinism is the sparsity. So here is an example with prefetching where the code for the prefetching is not shown but is there in comments. So the assumption is that we will have a smart DNN compiler. There are many such compilers in the market, and what they will basically do is that they will add this code to prefetch data from the lower level. So if you are going image wise, we can load the nth image in the DRAM, and then if you are going in the tile wise, say load the output tile in each local buffer. And then since for each output tile we are iterating through the input channels, in the global buffer we load both the filters as well as the IF map. So this is an output stationary architecture that we are looking at. So once the filters and the IF maps are done, all that we do is that we stream the data as we have seen earlier in our hardware architecture section. We stream the data and we basically stream the filter weights, we stream the inputs, they collide at exactly the right points, and then the output OF map tiles values are computed. So what you can see is that the compiler has a very important role to play over here because its job is to insert these prefetch statements at exactly the right points such that data is brought in just before it is meant to be used, such that you are not displacing good data, but you are still bringing in data that you will use in the future at exactly the right points of time, and then they will be used and then they will be discarded. So that is where stationarity is also coming into play. So now that we have appreciated the compiler aspects of running a DNN, in the sense good compilers are needed precisely for generating such kind of prefetch code and also for distributing them across the compute units, let us look at other kinds of unconventional hardware for realizing CNN computation, mostly interference. Most of the work in CNNs is about interference because the training can be done in software and can be done on a large high performance cluster. But the interference is exactly what happens on the device. So instead of using digital circuits, we can use analog circuits where we will use the electrical parameters of the devices to actually realize a multiply and accumulate operation. What's the main operation? The main operation is that you have a bunch of filter weights, a vector basically, because I'm converting, even if it's 2D or 3D, I'm converting it into a vector, right? Kind of like going this way. And then you have a bunch of input pixels. You have to do a pairwise multiplication like a dot product, and then you will have to add up all of these partial products to get the final value of the convolution. So the main aim is given two vectors, a vector of weights and a vector of inputs. So it could be 2D, 3D, 4D convolution, doesn't matter, but finally you are taking two 1D vectors, doing a pairwise multiplication and adding. That's the basic primitive. So we need to design an analog circuit to do precisely this. There are two approaches called charge sharing and current summing, which will basically realize the same thing, which is a series of multiplications and then an addition. That's all that we need to do. So charge sharing, the idea is that you have these multipliers and then you add them. So then how are we going to do that? So how we are going to do that is like this. So what we will do is we'll construct an analog multiplier. There are many ways of constructing an analog multiplier to multiply this xi and wi. One such approach is that we can use the equation for capacitance, which is the charge is a multiplication of the voltage and the capacitance. So in this case, one of these values could be encoded as the voltage, one of these values could be encoded as a fixed capacitance. And then at runtime, you don't expect the filters to change, but you expect the inputs to change. Hence, the filter could be encoded as the capacitance and the input as the voltage, where of course, as the input changes, the voltage would change. So this is where, quantizing it to a few levels or using a binary CNN will turn out to be helpful. In any case, once, this charge is generated, right, and it is kind of stored over here, right, on these capacitors, which are essentially in parallel. So capacitors in parallel, the capacitance basically adds up, right? So that is the equation. So what we are doing is that we are doing charge sharing, in the sense this will deposit some charge here, some charge here, some charge here. So charge is going to get shared, right? And it is going to raise the voltage of this common line over here, right? Let us refer to this as the bit line, same as memory. It will raise the voltage of the common line over here based on the total amount of charge. So there is a summation operation over here, which is basically a sum of products. This is a product, this is a sum of products. So then it will raise the voltage of this, and you can say it is roughly proportional to the additive sum over here, right? And so the total charge can be made, the total charge and the voltage over here, of course, that will depend on the parameters of this circuit, but it can be, the circuit can be kind of massaged to make it a simple relationship by changing the parameters. But the crux of the idea is that this voltage can be measured with an ADC. So with an ADC we can do that, which is nothing but an analog to digital converter. So that given the total charge, it will basically raise the voltage of this, that you can measure and you can convert that to a digital value, which is nothing but kind of an approximation of the sum of products or the convolution, in other words. So in this case, what we are doing, instead of using a heavy multiplier that is slow, what we are doing is that we have many of these light multipliers. We are using the analog nature of the circuit, which could of course bring in errors and inaccuracies. I am not discounting that. But if you are willing to absorb some of it, because CNNs are approximate circuits to begin with, then basically this is a very quick method of doing a multiplication, letting the charges accumulate, get shared, right? And the values of these capacitances are the same, then of course the voltage is the same, so finally the charge across them will also be the same, so the charge will get distributed. So you can work out the math, but essentially the total charge will determine the voltage over here, and the voltage over here will get converted to a digital value which is representative of the final output of the convolution. So this is an extremely power efficient and performance efficient way of realizing a dot product. Of course, the flip side is that the values of the capacitances have to be changed if you're changing the weights. But if, let's say, the CNN is fixed, this is not a very impractical idea. So this is a neuromorphic circuit because it is realizing a neural network. What we could also do is we could rely, instead of the capacitance equation, on Ohm's law. So in this case, V times 1 by R, V times 1 by R, or the conductance, is equal to the current. So basically in this case the voltage could be one value and 1 by R, which is the resistance, could be one more value. In the sense the voltage could be the input, 1 by R could be the weight. So then what you do is we set the voltages and then 1 by R is the weight. So they are getting multiplied. So that is the current, and then in series the current will get summed. So we are doing current summing. We are not sharing the current unlike charge, but we are summing up the current. And why is that happening? Because we are setting the voltage and this is V into 1 by R. So that is kind of the current over here, because mind you, this entire line is set to the ground potential. So that is why we are generating current which is going down. The current is getting summed, which is nothing but the sum of products. Right? The sum of the current, and each current is a product, so it's sum of products. This is effectively a dot product. So then what I do is that I measure the voltage across the test resistance, and this voltage is again converted to a digital value which is representative of the final convolution output. This is again, it has the same advantages of power efficiency and performance efficiency. Implementation technique, either use regular CMOS transistors where you are running it in a linear region. So linear region will allow you to do this multiplication, or as we have shown, use resistances and use capacitances. One more important thing that we saw in the chapter on memories, especially non-volatile memories, was RAMs or resistive RAMs, where the resistance itself can be varied. So one problem was that you want to realize a different weight, you have to vary the resistance, right? So what we had seen there is that the resistance of the cell can be varied by essentially changing the voltage across it. So the resistance is a historical function, or is a function of the historical values of the voltages. So this can be varied. So we can use such cells to kind of make it a programmable neural network, and then we can use charge sharing, current summing, etc. to realize such kind of neuromorphic circuits. This is always the happiest slide. So we have reached the last slide of this chapter, and also the last slide of version 1 of the book, which is that CNN based neural networks are becoming extremely popular ML techniques. What we have seen is that even though the fully connected layer, the FC layer, is the most performance hungry, but because we have only one or two of such layers, it actually doesn't make a big difference. And the pooling and ReLU layers are fast anyway. So the convolutional layer is the one that is the slowest and the one that determines the performance. Hence, we put in all our focus on this layer. We can have different kinds of stationarity. We developed a notation for the 7 loops: input stationary, output stationary, wait stationary, row stationary. We brought in concepts of tiling, of caching, of parallelism. All of that came in through our notation. How to realize it on hardware? Well, we said either you go for the direct product method, which uses a W block circulant matrix, or you use arrays. So arrays can again be of two types, systolic and semi-systolic. Semi-systolic ones are good when you start to design because they're kind of intuitive, but they rely on broadcast connections or tree of adders or something like that, which is not something to our liking. So we can use the retiming lemma to convert it into systolic. But a problem with the retiming lemma is that these arrays can become slow, in the sense you can slow it down by 2x or 3x, but that's fine. Multiple convolutions can be computed at the same time, so the throughput will increase. Then again, neuromorphic circuits can be made, right? So you do all your optimizations that you want to do on the model, prune it, quantize it, etc. And neuromorphic circuits can be made, can be constructed, right, using either RAMs or resistors, capacitors, transistors, and you use charge sharing and current summing. That's it, folks.